Okay, not that I rant about squaring real numbers a lot, but I rant about squaring real numbers a lot. And the fact of the matter is, and we discussed this on Monday, if I have something like this, and A is an element of the real number, so it's a real number, it's a number that's on the number line, then if I square that real number, I'm going to get a positive every single solitary time. And so I see this on the internet. I tell you about, these things coming up in my Instagram feed. As a matter of fact, my son sent me one via text. What's the answer to this? And I told him how to do it. But I see these show up on my Instagram feed, something like this. And there will be an argument in the Instagram comments that that's 4, and it's not. That's -4. So what's the difference between -2 squared and -2 squared? The parentheses indicate specifically that you want to square that number. So that is 4, that is -4. Because what the first one says is it says to square 2 and then change the sign of it, make it negative. So if you square a real number, it will be positive, but you can change the sign of it by putting a negative in front of it. So I have included in the slide deck in Canvas some perfect squares. So 0 squared is 0, 1 squared is 1, etc. And it is my humble opinion that you should know these. You should know that 3 squared is 9. You should know that 9 squared is 81. Now, I also think you should know 11 squared is 121, and 12 squared is 144, and 13 squared is 169. And then I kind of lose it after that. 14 squared is 196, I think. And 15 squared is 225. So I get up to about 15, and then I don't know. But I think you should know 0 through 10, what the square of that is. Conversely, I think you should know what the square roots are. So what is a square root? Well, the square root is the number that you multiply it times itself to get a value. So the square root of 4 means what is the number I multiply times itself to get 4. So that is what? 2, because 2 squared is 4. And that symbol means square root. And it actually means the principal, and I think it's an LE. Is it a PAL or a PLE? I don't know. And it means the principal square root, which means that it's positive. So when I take the square root of something, I get a positive number. And I think you should know the square roots of numbers 0 through 100. So I think you should know, and I'm not talking about, the square root of 2 is 1.414. No. If it's a perfect square, I think you should know what the square root of it is. The square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. What's the next perfect square? 9. Square root of 9 is 3. What's the next one? 16. Square root of 16 is 4. What's next? Without looking, 25. Square root of 25 is 5, etc. And the reason you should know this is it helps you in simplification of radicals. Now, by rule, by the laws of exponents, if I have the square root of a product of 2 numbers, I can write that as the product of the 2 square roots. So I don't know why you'd want to do this, but you could. The square root of 6 is the square root of 2 times 3 is the square root of 2 times the square root of 3. They're all the same value. And you can prove this to yourself by just doing it on your calculator. So if you want to show that the square root of 6 is the square root of 2 times the square root of 3, you can do that. So the square root of 6 and the square root button is above the x squared button on your calculator. The square root of 6 is 2.449489743. And it is a decimal approximation because this is an irrational number. So if I take the square root of a number that's not a perfect square, that's going to be irrational. Now, what's the square root of 2? And I have to arrow out of the square root times the square root of 3. Well, it better be the same thing or math falls all apart. So what does this benefit us, this particular rule? Well, what it helps us with is simplifying radicals. And I got into a philosophical discussion with a colleague just recently about the necessity of simplifying radicals. And there actually are calculators available for a very reasonable price that will simplify radicals. The TI-84 is not one of them. And so we got into a philosophical argument because they have told the testing center that students can't use the TI-30SX something. And it's a calculator that I've seen high school students in Oklahoma carry around with them constantly. And the reason they carry that $30 calculator is because it can simplify radicals. So they don't allow it to be used in the testing center. And so I got into a philosophical argument. I said, I don't care if they know how to simplify radicals at the college algebra level. And it's like, because what's the point of writing 75 is 5 times the square root of 3 with a calculator in your hand? I don't know. I don't know. Now, I understand in upper levels, if you get to calculus, you may have to simplify a radical, but at that point in your career, you'd have to simplify a radical that contains algebraic expressions so that you could integrate it. So, or take the derivative of it. So at that point in your career, you probably need to know how to do this. Well, even then, I'm not sure that you have to know how to do this. It's one of those, I'm getting long-winded here, but it's one of these things that I'm not sure how much we need it anymore, but we're going to do it anyway. So what we do, what's that? The simplifying of radicals. And so on a test, I don't get real tense about this. If you don't, as a matter of fact, I have encouraged classes not to try to simplify the radical because you make mistakes doing it. And if you just leave the radical alone, it's a perfectly valid answer, in my humble opinion. Now, there are professors on campus that disagree with me. So I'm going to show you how to do it. So what you do to simplify a radical is you look at what's called the radicand. And the radicand is the thing underneath the radical symbol. So in the first case, the radicand is 75. And you think to yourself, does 75 have a perfect square factor? So look at these perfect square factors. That is the second column. Will any of those divide into 75? 25, because 75 is 25 times 3. So that's what you do. You go over here on your table and you say, are any of those numbers in the second column a factor of 75? And yes, 25 is. Now you might guess 9, but you divided it. You take a calculator, divide 75 by 9, and it's not. But 25 is. So I can write 75 as, take 75 and divide it by 25. Do you get 3? So we can write this as the square root of 25 times 3. Okay, now using that property that we had on the previous slide, we can write this as the square root of 25 times the square root of 3. So the square root of a product, we can write as the product of the square roots. What's the square root of 25? 5. So is this 5 times the square root of 3? And they're saying exactly the same value. And again, in a class such as functions and modeling, where you're actually looking at real life situations, I doubt very seriously that you would tell your boss the answer is 5 times the square root of 3. Your boss goes, what? Well, can you tell me the decimal equivalent to that? Okay, but we're going to do it anyway. So now we're going to look at 54. Sure.
Say 9.
You say 9? What's 54 divided by 9?
6. Yeah, 6.
Is that right? Very good. So they taught you this in New Jersey. We're proud of New Jersey. I'm not sure how much in Oklahoma did you do this? See?
I feel like this is just high school all over again.
It is. It is high school. Did they teach you this in Mexico? Probably. Doesn't remember. Okay, so then what do you do?
They're both 3.
We don't want to go that far. We want to write this as a product of the square root of 9 and the square root of 6. Now, what's the square root of 9? Is that 3? How about the next one? Ooh, that's a big number, 304. And this is where a calculator comes in handy. Now it is divisible by 4, but I got a stinking suspicion it's going to be a number bigger than 4. That's a perfect square factor. How about 16? Is 16 divisible? No, actually, I think it is 4, isn't it? I got in my notes, it's 4. It's not divisible by 16. So it would have to be 4, 16, 36, 64. It has to be an even one. So is it divisible by 4? Is it 4 times, what's it, 4 times what? Is divisible by 16? It is divisible by 16. Helps if you, 16 times 19? Okay. I was just seeing if you were awake. So is that the square root of 16 times the square root of 19? And the square root of 16 is what, 4?
So that's like the last, that's how our homework will want to be answered.
Exactly. And where we see this in algebra is when we're using the quadratic formula to solve quadratic equations, which we're going to do at 11 o'clock. And the quadratic formula is a formula. And anytime you have a formula in mathematics or science, it's just got a bunch of letters and you plug in the numbers that represent the variables and you get a result. So the quadratic formula gives you a result that looks something like this, where you have a division of a real number, a rational number, and an irrational number, a square root, over a number. That's what the quadratic formula form ends up to be. So they're going to require you in your homework, if you have a radical answer to a quadratic equation, to write that as a simplified radical. So you just have to simplify the square root of 18. And you cannot divide these by 3 because the square root of 18 is actually equal to 18 to the 1/2 power. By definition, that's what the radical is. So I can't just willy-nilly divide that by 3 because I have to raise that to the 1/2 power before I could divide it by 3. So I can't do that. So what perfect square factor is there in 18? Is 4? No. Is 9? 9. So is it 9 times 2? So then we're going to simplify that. That is 15 plus the square root of 9 times the square root of 2 over 3. That is 15. What's the square root of 9? The square root of 9 is 3. 3 square root 2 over 3. Now, can I cancel a 3? And the answer is yes. Why can I now cancel a 3? Because 3 will go into 15. It will also go into 3. So can I cancel it? Yes. So is this 5 plus the square root of 2? Okay, so this leads us to this kind of problem where they ask you to simplify radicals by adding them together. And again, you're going to have to simplify the square root of 20. Does 20 have a number as a factor that's a perfect square? Is it divisible by 4? Yes. So is it 4 times 5? So this is -9 times the square root of 5 plus 7 times the square root of 4 times the square root of 5. So the square root of a product we can write as the product of the square roots. So this is -9 times the square root of 5 plus 7 times the square root of 4 is 2. 2 times the square root of 5. So is that -9 square root 5 plus 7 times 2 is 14. And now these are like terms, and I'm using quotations because they're like terms because both of the terms contain a coefficient and then a part, the square root of 5, that's a common factor to both of those. So we can combine the coefficients in that case because we can use the distributive law. So this is technically -9 plus 14 times the square root of 5. So we can add the coefficients just like if the square root of 5 was an X or a Y or something like that. Okay. If it's good, you have to let us all listen to it. All right.
That was.
No, I probably don't. My musical tastes kind of run to, no, I do not like country at all. No, actually, 80s rock. My favorite band is Tears for Fears.
Yes, with yours?
Yes.
So you like Beatles?
Yeah, yeah.
That's good too?
Yeah.
That's older than 80s, right?
Oh, that's 60s. Yeah. But I'm old enough to remember the Beatles. Yeah. But Tears for Fears, that's my favorite band of all time. Yeah, it's different. And Journey and those, 70s rock was my heyday, and the early 80s rock. Okay.
Okay, like.
I don't like hip hop.
How did you say you like?
No, rock. No.
So you don't like the old rap either, nothing?
Some rap. I'm not. No. I'm more of some of that's. I'm not in that demographic. Would you agree? I'm not in the demographic of a lot of hip hop. You never know. That is correct. Because you thought I liked country. And I do not like country.
I thought everybody else.
No, no. All right. So let's get back to my rant about squaring real numbers. And again, if you square a real number, the result of the squaring of a real number will always be positive. But is there a number that you can square and get a negative? And the answer is yes, but it's not real. So what's the opposite of real? Not real. And what word do we use? What's imaginary? And do you know that Carl Friedrich Gauss, the guy that came up with this, that's why they named these numbers imaginary? Because they weren't real. So is there a number I can square and get a negative value? And the answer's yes, and it's called I. I is the imaginary unit. So this is a definition for you. This isn't, I know that if I got 1 and 1, I get 2. This is a definition of a new number system, the imaginary number system. And the imaginary unit, I, is equal to the square root of -1. And so we need these numbers because, as you saw earlier with that simplification of a radical, the answer that we can get from using the quadratic formula can include square roots. And there's no reason whatsoever the thing underneath the square root can't be negative. Now, in real numbers, that doesn't exist. The square root of -4 in real numbers doesn't exist. But in imaginary numbers, that's 2i. So let's give ourselves a definition of the imaginary unit. The imaginary unit, I, is the square root of -1 by definition. So if I square both sides of that equation, I get I squared is equal to -1. Poof. Now you have a number that you can square and get a negative. It's the imaginary unit. So using the imaginary unit I, we can express the square root of any negative number as a real multiple of I. And I'm going to cheat and tell you that if it is a perfect square, your calculator can do this. Now, what it can't simplify is something like the square root of -75 because your calculator doesn't simplify radicals. But it can take the square root of -16. It can do that. Okay? So the square root of -25 is the square root of 25 times the square root of -1. The square root of -1 is I by definition. Square root of 25 is 5. So the square root of -25 is 5i. 5 times the imaginary unit I. So by definition, if you've got the square root of a negative, that is equivalent to I times the square root of whatever b is. So the square root of -16 is 4i because it's the square root of 16 times I, and the square root of 16 is 4. Which is the next slide. Okay, so what's the square root of -130? Well, my calculator will give me a decimal approximation to this. It's some number times I, but it won't give me an exact value. To be able to get an exact value, I need to simplify the radical. So this is by definition the square root of 130 times I. That is by definition, the square root of a negative is whatever that square root is times the imaginary unit I. By definition, that's what it is. Okay, now can I simplify the square root of 30? Will 4 go into it? Nope. How about 16? No, not if 4 won't go into it, 16 won't go into it. Do I have it written down? I have no idea. It's 13 times 10. I think we're done. I don't think there is any perfect square factor in 130. Can you think of a perfect square factor of 130? I can't. It's 13 times 10, but neither one of those have perfect squares in it. So is it 13 times 2 times 5? There are no perfect squares there. So I think we're done. It's the square root of 130 times I. And typically, we write this as I square root 130. And the reason we do that is because we want to illustrate that the I is not part of the radicand. It's not associated to the 130. It's outside the radical. So typically, if it's outside the radical, we write it first. Okay, now since these are numbers, well, let me go back a step. Okay, so if I take the set of imaginary numbers, and what makes it an imaginary number is if it contains the square root of a negative somewhere. and I combine those with the set of real numbers, I get this set of numbers called the complex numbers. And it's called complex not because it's difficult, it's because it is the marriage, the joining of two different, completely different number systems. So if I take the real numbers and combine those with the imaginary numbers, then I get this set of numbers called the complex numbers. And now you got every number system you ever need. So the way we write a complex number is we write it as the real part plus the imaginary part. And A and B are just real numbers. They're just numbers that are on the number line, and they can be positive or negative. It doesn't matter. Okay, if A is equal to 0, then BI is a pure imaginary number. If B is equal to 0, then that's a real number. So every real number is complex. Every imaginary number is complex. Okay, since they're a number system, you can add, subtract them, and multiply them and divide them. And your calculator will do this. So should I show you that your calculator will do this? You have to do something to your calculator to get your calculator. Okay, let me switch over to my calculator. All right, so on your calculator, right next to your second button, just to the right of it, is your mode button. And if I go to the mode, you can see if I arrow down right here, do you see where my mouse is moving back and forth? I have that I can set my calculator to real numbers, only deal with real numbers, or I can set it to calculate with complex numbers. And that is the A plus BI. A plus BI is a complex number. It's a combination of a real number A and an imaginary number BI. So B times the imaginary unit I. So you can go down there and highlight the A plus BI, and then you can do these calculations on your calculator. Just one time and you're done. Unless you reset your calculator for any reason, and you'll have to redo that. So, for example, if I want to take the square root of -16, which we did earlier, that is 4i, correct? It's 4i. So your calculator will do all of these calculations for you. If it can add, subtract, multiply, and divide real numbers, it can add, subtract, multiply, and divide complex numbers. All right, so if we go back to our slide, here is an example of adding to complex numbers. We have the complex number 5 minus 2 times the imaginary unit I, so 5 minus 2i, and we're adding to that the complex number 3 plus 3i. Now, you should be able to do that one in your head, because to add complex numbers, you add the real parts, and then you add the complex parts, or the imaginary parts, excuse me. So is this 8? Is this 8? Come on, computer. Plus I. So 5 and 3 is 8. -2 plus 3 is 1 times I. And this one's a little more complicated, so you may break out the calculator for this one, and we will in just a second, because what I saw on the last test is notorious for algebra students across the United States. If you have a negative outside of parentheses, you very well and good negate the first number inside parentheses, and the rest of them you just forget about. But if you have a negative outside of parentheses, that means you are subtracting everything on the inside of parentheses. Now, the way I learned it way back when in the olden days is if there's a negative outside of parentheses, you change the sign of everything on the inside of the parentheses. That is the directions that I got. So what is this going to be? 2 minus 12 is minus 10. 6 plus 1 is 7i. But again, your calculator can do this, so if you're nervous or you want to check, you can go over here and let your calculator do it. Okay, so we had there it is. 2 plus 6i, and I don't need to put that in parentheses. Now, where's the I located? The I is located above the decimal. So you go second decimal to get the I, and then what are we doing? We're subtracting, and I'm going to put that in parentheses. 12 minus I, 12 minus second decimal close. Is that negative 10 plus 7i? Is that what I got? It's nice to know that the calculator verifies the calculation that I did. Okay, and you can multiply these two. To multiply these, we use the distributive law. And we remember that when we're doing this multiplication, that by definition, I squared is the real number -1. By definition, that's what the imaginary unit squared is. So if I use the distributive law, what do I get? 7i times 2, is that 14i? And then I have 7i times minus 9, is that minus 63i squared? I times I would be I squared, but that's what? That's -1. So what does that do? It changes the sign of that to a positive. So that's 14i plus 63. And then Pearson can be really picky. And it wants you to write the real part first and the imaginary part second. As a matter of fact, if you do this on your calculator, it will write it as 63 plus 14i. So it will put it in standard form. This is standard form where the real part comes first and the imaginary part comes second. What's this next one? Well, we're going to FOIL it. So 5 times 6 is 30, correct? What's outside? 5 times minus 7 is minus 35, but we have an I there. Inside is what? Plus 4 times 6 is 24. I, and then last, what do we have? 4 times -7, is that -28? I squared, but that is -1. And then what does that do? That changes that sign to plus. So we have 30 plus 28, is that 58? Minus, what do we have? Minus 35 plus 24, is that minus 9? No, 11. 35 minus 24 is 11, isn't it? And real quick, let's run over to the calculator and let's do this one. Okay, parentheses. 5 plus 4i, 5 plus 4 second decimal place, close those parentheses, open the parentheses for the next complex number, 6 minus 7i, correct? Close those parentheses. 58 minus 11i. Now, the equality of complex numbers, if two complex numbers are equivalent to each other, that necessarily means that the real parts have to be the same and the imaginary parts have to be the same. So if you have a plus bi equals c plus di, a and c have to be the same thing, as does b and d. Yes, sir.
Do like part drive, remember, and it's like the two subtraction. So for the top, but when it has I in it, top subtraction does it?
It could have I in it.
So would that be -1 too?
No, I squared is -1.
Um.
And we're gonna do some examples at 11 where we use the quadratic formula and we get both a perfect square, so it's just an imaginary number, and we get one that's not a perfect square. So we'll do that at 11, where we look at some examples of them.
Yeah, I have a question too, is are these the only people in the review class?
No,
The people-
there's one more. There's only 5 of you, yeah. And I pondered why that was, because usually this class is fairly full. And so I went to the head of the math and science department and and as I was talking to her, the head of the agricultural department, Professor, her last name just left me. But anyway, she said, "Oh, that's because your class is offered at the same time as something out at the Royce Ranch. And so since this class is being offered at the same time as ag classes, all my ag students are taking it. And usually this is a class that the ag students take. It's a practical class it's a little bit more practical than college algebra because we do a lot of real life examples.
That really helps with like the exams and stuff.
Yeah. All right, so exponents. This is pure review. An exponential expression, if you have a number raised to a power, that simply means to use that number as a factor that many times. And here are your laws of exponents. And if you don't remember them, then I recommend you print this slide off. And this is what slide is this? This is slide 3 in the slide deck for the 3-3 review. No, actually, it is 1. And the reason it's 1 is the way that division works. So it deals with this property right there. So if M and N equal the same number, so let's say M and N are the same thing. So we have A to the M over A to the M. Well, that's 1, is it not?
Yeah.
But it's also equal to A to the M minus M, which is A to the 0. So any real number except 0, if you raise it to the 0 power, you get 1.
Yeah. But and that's just and then yeah, how could they be like how could they be like terms? Like they aren't
Okay, let's say 2 squared divided by 2 squared. What's 2 squared divided by 2 squared?
well one.
1. But by definition, if I divide like bases, I can subtract the exponents. That is a definition of exponents. If the bases are the same and you're dividing them, you can subtract the exponents. 2 minus 2 is 0. All right, so let's use these properties to simplify some exponential expressions. Okay, we have x to the 4th times x squared. What is that?
X squared. Oh no, x to the 6th.
X to the 6th. Because if we multiply like bases, we add the exponents. How about this one?
What does that say at the bottom?
X to the 8th.
X to the 6th.
Same thing, x to the 6th. Because if you divide like bases, you subtract the exponents. Okay, how about this one? What do you do here? Okay, and what you do, kind of distributing, is you raise everything to that power. So you raise 3 to the 5th power, b to the 5th power, and y to the 5th power. What's 3 to the 5th power? 243? How did I know that 3 to the 5th is, because I know 3 to the 4th is 81, because 3 to the 4th is 9 times 9. Take 81 and multiply that by 3, do you get 243? I've been doing this a long time. It's not that I'm brilliant, it's just that I've been doing it a long time.
I was at the tutor, festival there, and he was, I asked him, how do you like just know like what to do on every single problem?
Practice, 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 practice.
Doing small life, and it's just, what it takes.
Practice, practice, practice. It's just like, how do you know when you're in the right place and you lob that ball up, it's gonna just go swoosh? Because you've practiced it, practiced it, practiced it, practiced. If I went out on a basketball court, even though I'm tall, and I threw the ball up, it at the same place that you'd make a 3-pointer, my ball would be 20 feet short. So it's just because I haven't I have the height to play basketball.
Yeah, you'd be nice at that.
I'll tell you the basketball story one of these days. Because I have one. And but I played very little in my entire life. So could I play basketball? Well, maybe if I'd practiced, but I never practiced, so I can't play basketball. But this I practiced a lot. So can I do it? Sure. Okay. Yeah, I got my Instagram reels. All right, how about this one? 3 over c raised to the 4th power. If you raise a fraction to a power, you raise the numerator to that power, and you raise the denominator to that power, and that's 81 over c to the 4th. Now you can also multiply if the like bases are real numbers. 5 to the 3rd times 5 to the 2nd, is that 5 to the 5th? Which I have no idea what that is. What is that? 3,125, and I would do that on my calculator for sure. And then if I raise again an exponent to an exponent, I multiply the exponents. If I raise a power to a power, I multiply the exponents. And it doesn't matter if the exponents are fractions, doesn't bother me a bit. This is x to the 1/7 plus 1/4. If you're not comfortable adding fractions, then let your calculator do it. Let your calculator add a 1/7 and a 1/4. I think that's going to be 4 plus 7, 11/28. Because I can't add those in my head because I've been doing this a long time. And if I raise a power to a power, again, I multiply the exponents when I do that. Is that x to the 11/4? Because the 3's will cancel. And if I divide, I subtract. I don't care that they are fractions. I don't care. Because I know my calculator can help me add, subtract, multiply, and divide fractions if it needs to. Okay, our last definition of exponents deals with negative exponents. And negative exponents have absolutely nothing to do with the SIGN of your number. Has nothing to do with that. What it has to do with is the reciprocal. So if you have something raised to a negative power, it means to take the reciprocal of that. So 5 to the -2 means, by definition, take the reciprocal of, that's what that means right there, reciprocal. Reciprocal of 5 squared. That's what it means. So what is 5 to the -2 equivalent to? It's equivalent to 1 over 5 squared. So when you got a negative, it means take the reciprocal. So that's what, 1 over 25? Now, if it's in the denominator, I don't care. It still means to take the reciprocal. So if I have 1 over 8 to the 5th, what do? I take the reciprocal by what? flipping it over. So is this equal to 8 to the 5th? Again, that's what that means. It means reciprocal. So you're going to take the reciprocal of the value raised to the positive power. So you're just going to flip it over. And I went on what, 8 to the 5th? I don't have any idea what that is. Don't care. Okay, so if I raise a fraction to a negative power, okay, so you could, by the laws of exponents, do this and then flip it over. But the easier thing to do is just to take the reciprocal of the fraction and raise that to the positive power. Can I do that? Yes, because that's what it means. This means reciprocal. That's what it means. So you flip that thing over and raise it to the third power, whatever that is, 125 over 8. And here, if I raise a product to a power, I raise everything to that power. Now, when I raise a real number to a negative power, then I'm going to actually have to do that. And then when I raise a power to a power, I multiply the exponents. -2 times -3 is +6. 5 times -3 is that -15. And depending on how my lab math wants the answer, that may be fine. But by definition, 2 to the -3, that means reciprocal. So that's 1 over 2 cubed, x to the 6th times what? 1 over y to the 15th. Is that x to the 6th over 8 y to the 15th? And this one, that again, that means reciprocal. So that's 1 over -6x to the 4th squared. Last problem. Last problem. What would you do here? Now I know what I would do. What would you do?
Oh, no. Distribute.
I'm not going to do that first.
Why?
I'm going to flip it over. So if that negative in the next to the 5 means reciprocal, I'm going to flip this over. And then you distribute. So you raise the z to the 5th power. You raise the x to the -4 to the 5th power by multiplying the exponents. So it's x to the what? -20. And then y to the 5th power. And then you can move, that's a minus there. You can move this up there because the negative means reciprocal. So you can move that to the top by taking the reciprocal. Is that z to the 5th, x to the 20th over y to the 5th? Now, you may have learned sometime in your previous career that you can move negative exponents from the numerator to the denominator by making it positive. That's because you're taking the reciprocal. Or you can move it to the denominator, from the denominator to the numerator by changing the exponent to a positive. Again, that's because it's the reciprocal. So you may have learned that particular rule. If you have a negative exponent in the denominator, you can move it to the numerator by changing the sign. If you have a negative exponent in the numerator, you can move it to the denominator by changing the sign. Any questions? We went through a lot quick, didn't we? So be sure you do your homework.
One.